So we're now going to talk about multivariate calculus. But before we go on to that, we want to talk about univariate calculus or single variable calculus. So this is the example we had, like f of x is equal to 2x squared minus 3x plus 5. So in order to find a max or a min, we wanted to do two things. So to find a minimum, we had the first order condition of f prime of x is equal to 0, and we solve for the x star, or the x that satisfies that equation. Second thing is we take the second derivative, plug in x star, and that's going to be not equal, but for a minimum it's going to be greater than 0. For a maximum, it's very similar. First step is f prime of x is 0. Solve for x star. Second order condition is the second derivative of x star is less than 0. So to apply it briefly to here, we have f prime of x is equal to 4x minus 3. We set that equal to 0. So x star is equal to 3/4. Now that's the x that's going to optimize, but we need to know if it's a max or a min. So we take the second derivative, which is just equal to 4. We evaluate it when x is 3/4. Well, there's no x there, so we don't have to worry about that. And we know this is greater than 0, therefore we have a minimum. So this is the box and the equations that we highlight of how we optimize an equation with a single variable. Well, now we're going to do something very similar, but we're going to have two variables. So we're going to have f of x and y equal to, we can come up with an equation, x squared plus 2x plus 3y squared minus 4y plus 5. So now we have this equation, and we want to follow through on the same steps. But now the difference is, here we had just one variable, so we just do f prime of x. Well, with two variables, we're going to do what's called a partial derivative. And what a partial derivative is, where before we had df of x dx, now we're going to write it slightly different. A curly d f of xy with respect to x. So what we're saying here is we recognize that our function has two variables, but we want to just look at how does our function change when x changes by just a little. We want to hold y constant. So that's what a partial derivative does. It holds y constant, so we can treat y just like a number. Another way to write this is f sub x. Well, if we take this, let's go ahead and take the partial derivative of this function. But now remember, we're looking when x changes, and y is just a number, so y doesn't change at all. So we take the derivative of the first part, 2x, plus 2. Now 3y squared. We're saying we're going to hold y constant, so that's just a number. So what's the derivative of just a number? Well, it's always 0 of a constant. We have another constant here. So the derivative of this with respect to x is 0. Now with respect to y, it's not, but here we're saying we want to take the derivative with respect to x. So that there is in our first partial derivative with respect to x. To do that with respect to y, we then signify that y is our variable, and we're going to hold everything else constant. So we're going to write this f sub y. So there's no y here, so that's 0. The derivative of that is 0. Now we have 6y minus 4. And so these are the partial derivatives. Now we can also do second partial derivatives by simply doing the partial derivative with respect to x, and then we can just do that twice. Okay, and so we signify this as f sub x. So that means we first take the derivative with respect to x, we get 2x plus 2, and then we take the derivative of this, just like we did previously, but treating x as the variable and y as the constant. So that equals 2. We can also do the second partial derivative of f of xy with respect to y. Well, this is the same as f sub yy. So we take first the derivative of y with respect to y. We get 6y minus 4, and we take the second derivative of this, which is simply 6. And now the question is, how do I know if this is a max or a min? So here's our box that we're going to write out. So with multivariate calculus, the first condition is that f sub x is equal to 0 and f sub y is equal to 0. Both of these have to be true. Second condition is that the second derivative, if it's a minimum, has to be greater than 0 for both of these. All right, so we have similar to this first order condition with a single variate model. The first derivative set equal to 0, solve for x star, take the second derivative. That's also going to be the same for here. Take the first derivative, set it equal to 0, but now there's two variables, so you have to do it twice, and both the second derivatives have to be greater than 0. For a maximum, it's going to be very similar. F sub x is equal to 0, f sub y is equal to 0. And the second order condition is f sub xx is less than 0, f sub yy is also less than 0. And so that's how we find the first and second order conditions and find an optimum, or the extrema, of a multivariate equation. So let's go ahead with this example now. So the first order condition is we set f sub x equal to 0 and f sub y equal to 0. And now we just solve for x. So here x star is equal to -1 and y star is equal to 2/3 or 4/6. So here's our x and y. Now we need to know, is this a maximum or a minimum? So let's look at our second derivative. Well, our second derivative is greater than 0 for both f of xx and f sub yy. And so therefore, we look at our equation here, and the minimum shows that we've satisfied this. F of x equals 0, f of y equals 0, f xx is greater than 0, f y is 0. So therefore, to optimize this equation, x star is -1, y star is 2/3, and we found a minimum of that function.